start. So it's a pleasure to have Andrew Appel from Princeton University. It is a pleasure to have Andrew Appel from Princeton University, and he will tell us about the proof assistant Coq.
Thank you. So Vladimir asked me to give a talk that's not so much a conventional research talk as more of a tutorial to introduce you to the flavor of what it's like to use this proof assistant to prove theorems about things. So I'll give a very abbreviated sort of summary of what it is one does. You want to prove a theorem, or I want to prove theorems. So you choose a logic in which to formalize this theorem, unless you're a mathematician, in which case you just skip right to proving the theorem. And then you choose a mechanical validity checker for your logic, which is a computer program. And you state your theorem in a language accepted by the validity checker. And then you use a proof assistant to construct the proof term, because proof terms are very technical, fiddly objects, and they're no fun to construct entirely by hand. And then you use the validity checker to check the proof. So I'll give an example of a project I did a few years ago. I had a big piece of software, a compiler, and another piece of software, a checker, and I wanted to prove a certain property of the checker software, which is several thousand lines of program code. And the theorem is that if the checker accepts a program that's the output of the compiler, then the program will execute safely. So that was the theorem I want to prove. I chose a logic, which is Church's simple theory of types, or higher order logic, 1941, except without the axiom of choice, because who needs the hassle of worrying whether you can trust that. And the validity checker is something, a little program called FLIT that I'll tell you a little bit more about. The language accepted by this checker, that is the logic, well, in some sense, is LF, the Edinburgh Logical Framework. So I expressed the axioms of higher order logic in the language LF, and the proof and the theorem. The proof assistant that I use to help me construct the proof is 12 by Frank Fenig's group at Carnegie Mellon. And then the FLIT program verifies the validity of the theorem. Now, in this picture, everything's to scale. That's 170,000 lines of code and the size of the checker. So here's the size of my proof. It's a big, hairy thing. There were a few PhD theses in here, because not only was there the expression of the proof, but there was actually some new mathematics to be done in the construction of this proof. And here, also to scale, are the size of what you need to trust. This is the validity checker. And this is the specification of the axioms of the logic, which is, I don't know, 10 lines, and the specification of what it means for a program to execute safely in that logic. And let me just blow up those two little pieces to a much bigger scale. And to specify what is the Spark machine was several, 1,500 lines of logic, and then the specification of modular arithmetic that the machine processes was a few, 100 lines, 150 lines, and so on. And then the program that checks validity of terms had a parser and a type checker and so on. So if you get this part wrong, then either you've proved the wrong theorem, which is pretty useless, or the validity checker might accept an invalid proof. So you have to make sure these are right. But then all those other pieces, if you get them wrong, you'll get caught by the validity checker. So that's the general scheme of things. And my current project is to do, I don't know, more of the same, except now we want to verify things about much more interesting tool chains and verify correctness properties instead of safety properties. And for this new project, I want to prove soundness and correctness of tool chain components. The logic will be the calculus of inductive constructions. The validity checker will be the Coq kernel. The language in which I express the proof is called the Coq vernacular, and the proof assistant will be the Coq tactic system. Now, the way proof assistants are generally constructed, and there are dozens of them out there, is they have two parts. There's the kernel, which checks validity of proofs, and which you better get right and you have to trust. And then there's the tactic system, or a whole bunch of algorithms and decision procedures to help you construct proofs. Well, that part is just software, and as such, it's expected to contain bugs. And if that part's wrong, then it will construct proofs that will not pass the validity checker, and you'll know. So, so there are all sorts of reasons to believe that the Coq kernel is trustworthy, and they have to do with, is the logic sound, and is the implementation correct? And there's all sorts of peer-reviewed publications by careful people on those issues. So I'm willing to trust it, at least for the time being. OK, so what is the calculus of inductive constructions? Well, Steve showed a little bit of that to you on Friday last week. You start with, basically it's an expressive logic based on type theory. We want expressive so that we can state and prove all the theorems of interest. And first order logics are just a bit too clunky for that. And we want it to be sound. In other words, the advantage of certain kinds of logics based on type theory is that they actually have models, and models that we can believe and understand. And I know many people that don't believe set theory. But I don't want to talk about that because I'm not a logician or a philosopher. What? Yeah, OK, fine. So we start with simply type lambda calculus. And then we add parameterization based on type parameters. And then we have type operators. And then we have dependent types depending on terms. And then we add inductive definitions. So as you can see, in the 20th century, logic advanced enough to be both expressive and trustworthy enough to do this with. And I don't think it would have been practical to do some of these things in the logics of, let's say, 1950. And then since about 1988, the software, not just Coq, but many other such systems, has been developed. So one of the reasons that Coq is usable is that it's a piece of software that a reasonably large team has been continuously developing for the last 20 years. And it's usable. OK, and lots of interesting things have been proved in Coq. So for example, the four-color theorem, there was this proof in 1976 by Kenneth Appel and Wolfgang Haken, in which many parts were automated because they were sort of 4 deep quantified formula on 15 things each, and there were 1,900 of them, and it was just too tedious to check by hand. And then there was a lot that wasn't automated, such as reducibility, so that when, let's say, Armin Haken gave a talk about this at Stanford in 1976, the mathematicians in the audience wondered whether you could trust the computerized parts, but the computer scientists in the audience wondered whether you could trust the parts that were not checked by a computer. So, Robertson et al. Did a proof 20 years later, which reduced the number of configurations down to about 600. And then Georges Gontier in 2005 used Coq to automate the entire proof end to end, so that now at least the computer scientists can trust the whole proof, and the mathematicians can't trust any of it. OK, so there's lots of other interesting things proved in this theorem prover, and then in other theorem provers, there's lots of interesting things proved also. But that's enough about sort of summary. Let me show you how Coq works. So I'll start from the beginning. I'm putting a few things in this playground module because I'm actually repeating definitions of things that are in the Coq standard library, and I don't want to shadow the namespaces. Oops. What did I do here? Here's an inductive definition of a set, or you can think of it as a type, containing 2 things, true and false. It's just an enumeration. There's a hierarchy of types, so that types at one level in the hierarchy are contained within types at the next level, and this avoids circularities that would lead to inconsistency. But Coq figures out which level of the hierarchy you need to be for any given type, so you don't have to say at which level you are. This is at a pretty low level because it doesn't depend on any other types. You can think of this as the axiomatization of a set with 2 elements. So true is an element of this new set called bool, and false is an element, and there aren't any other elements. And you can use that fact in your proofs too. So here's a command that says, tell me about true. True has type bool. There's another thing out there, true with a capital T, which has type proposition. Propositions are quite different from Booleans. So here's a proposition. There aren't just two propositions. They don't all collapse to just true and false. And propositions, you can think of this proposition is the type of all proofs of this proposition. But this thing, true with a lowercase t, is just a thing. It has very little semantic structure. OK, well, that's an inductive definition, but it's not very inductive since it doesn't have any recursion. So here's a slightly more interesting inductive definition, which is the structure of natural numbers with something capital O, which we'll call 0, but it's just capital O, of type nat, and S, which is a function from nat to nat, and nat is a type. So now there are just two constructors. Any nat must be built by some finite application of these constructors. So it's inductive. If you want to build things with infinite applications of constructors, you can do that too. That's co-inductive. I never use that because I don't need to. And nobody would use co-induction if they don't need to. All right. So now we can make definitions. So what's interesting in this definition? First, there's a kind of expression that you can use on inductive things. It's the case analysis. N is built using one of these things. And this is a function from natural numbers. So there's the parameter type, the result type, the name of the parameter. If n is O, then return O. If n is S of O, return O. And if n is S of some variable n prime, return n prime. When you make a case analysis, then Coq will check that it's exhaustive. It covers all the cases. And if there are overlapping cases, then it'll just take the first one in the list for any given value. So this one doesn't seem to have overlapping cases. So that's what -2 is. The green stuff is theorems and definitions and so on that Coq finds are well typed and therefore should be accepted. What's the type of S of S of S of O? It's 4 : nat. So there's notation, fancy syntactic sugar, that will print out in a nicer form and even accept as input in a nicer form these constructions, which get tedious. But the notation doesn't change what the thing really is. And there's a notion of simplification, that we can unfold definitions and actually apply the case analysis to actual structures. And if we evaluate simplification in the term -2 applied to 4, we get 2. So we can do very simple computations on finite structures. So what is S? S is a function from nat to nat. Well, it's more than just a function, though. It's a constructor. That is, we can do a kind of injection on S. We know that any nat is either built with O and or with S, and if it's built with S, we can extract the underlying natural number. So constructors are functions that have this extra property. -2 is not a constructor, it's just a function, and we can't hope to do that kind of intentional analysis on it. Pred. I shouldn't even be talking about pred. I'm getting something here when I check pred from the standard library. But here's -2. -2 is a function from nat to nat. And I don't know, -4, which does pattern matching on -2, illustrates that Coq doesn't really like it when we treat an ordinary function as if it were a constructor. Not allowed. So here, there's the error message window. And one of the things that therefore keeps us honest in any kind of proof assistant is that it won't accept logically ill-constructed things. OK, so let's leave that as a comment. That definition of -2 was not recursive, but we can also make recursive functions. So even b is a test that tests natural numbers for evenness and returns a Boolean. That's what the b stands for here. And if n is 0, return true. And if it's successor of 0, return false. And if it's successor of n prime, return even b of n prime. Now, Coq remarks that even b is recursively defined decreasing on the first argument. Every function you can write down in Coq is total. And that helps you avoid logical problems when we talk about values that don't actually exist. Functions in most computer programming languages of interest are not total due to certain unfortunate results of Gödel and Turing and so on. So when you write a recursive function like this, Coq checks that at least one of the arguments is structurally recursive. That is, the recursive call to even b here is on a term that's a structural subterm of the original term. Since any inductive construction must be a finite object, then this recursion must be well-founded. OK, and so here's a non-recursive definition of oddness that calls upon the definition of evenness. And now here's a theorem, which would be more straightforward to say the word theorem here, which I could have done, or I could have said lemma or example. Mathematicians like to use lots of different words for the same thing. And the theorem is that odd b of 1 equals true. And here's the proof of that theorem. So that when we're proving a theorem, this window is of interest. Above the line are all the hypotheses that we can use at the current point in the proof. And below the line is the proof goal. And so here's the proof. We apply the simplification tactic. So that's the application of a tactic in the middle of a proof state. When we simplify, that wasn't very interesting. Let's do unfold odd b. OK, odd b unfolds to neg b of even b, as expected. And if we unfold even b, what happened? The even b of 1 unfolded, and then the case analysis took effect immediately. And the case analysis on 1 for even b gives us the Boolean false. And then we can simplify, which the simplify is really just going to unfold neg b, which is defined somewhere as a case analysis on Booleans. Now we have to prove true equals true. And there's a tactic called reflexivity, which applies the appropriate axiom about equality. Well, equality is itself just an inductive definition with one constructor, which maybe I'll get a chance to show you. So let's see. Reflexivity is a pretty powerful tactic, and it will unfold things and simplify as necessary. And it finds that with enough unfolding and simplification, odd b of 4 really is the same thing as false. OK, so now we can define some functions on natural numbers. Here's addition. So I want to do the plus of n and m. And if n is 0, return m. Otherwise, if n is successor of n prime, return the successor of the recursive call plus n prime and m. And now Coq remarks that plus is recursively defined decreasing on its first argument. So if it's decreasing on at least one of the arguments, then it must be well-founded and a total function. So we can prove the theorem that 3 plus 2 equals 5. So if we unfold plus and do all the case analysis, it turns out to be that 5 equals 5, which we prove by reflexivity. So here's multiplication defined using the same principle. Here's minus. Well, minus is pretty bogus on the natural numbers. As you can see, there's the question of what to do when one thing is not bigger than the other, and you're required to have a total function. So there are various design choices here, but this one is a fairly standard logical hack of saying that 6 minus 8 is 0. Well, all right, so we have a minus that doesn't have all the most beautiful properties in the world. And I put this in this little playground just because minus and plus and times are actually defined in the standard library, and I want to use the standard definitions. And they're defined exactly the way I've shown here. OK, so what can we say? A mult of 3 and 3 simplifies to 9, which is equal to 9. Now we can add some syntactic sugar, as it's called, notation, that when I write x plus y, what I really mean is the plus x and y as defined above. So we're going to construct arithmetic. It's not really built in to the system. And then I can check 0 plus 1 plus 1. And Coq says, well, the type checking of 0 plus 1 plus 1, it's a nat. What?
Level 50?
Oh, well, you know, some things bind tighter than others in the notation. We want star to bind tighter than plus in our mathematical notation, so it must be that 40 is tighter than 50. Now, I use enough different systems that if I want to remember whether the lower numbers bind tighter or not, I have to go look up whether plus binds tighter than, whatever. OK, so here's a theorem. For all n, 0 plus n equals n. So this theorem has a quantifier in it. And the tactic intros will introduce some quantified things, and give them names. So I want to introduce the quantified thing and give it the name n. And when I do that, the n moves above the line. It's now an assumption. There's assumed to be something called n, about which I know all the things above the line, which is to say not much, except that it's a natural number. And now I need to prove that 0 plus n equals n. But if I were to unfold plus, I would discover that plus does case analysis on its first argument, and its first argument is 0. So by simplifying, I just get n equals n, which is easy to prove by reflexivity. That's a theorem. OK, here's another theorem. If n equals m, then n plus n equals m plus m. And we prove that. We introduce the two quantified things. And now we have an implication.
So if in the previous one you would have asked to prove that n plus 0 equals n.
I'll get there. Give me 2 minutes. OK, but it would have been longer. I would have to use induction. All right. Here's an implication. And so what I can do is I can assume the antecedent and prove the conclusion. And assume the antecedent means intro is h. Move the antecedent, n equals m, above the line and call it an assumption, a hypothesis, h. H stands for hypothesis. And now there's a tactic rewrite that says you can take any theorem or lemma or axiom or hypothesis that's an equality and rewrite the occurrences of the left-hand side into the right-hand side below the line. And really, this is a consequence of sort of Leibniz equality. All right, so now we have m equals m equals m equals m, m plus m equals m plus m, which is proved by reflexivity. OK, so here I want to prove that 0 plus n times m equals n times m. And here's an example of doing rewrite not by a hypothesis, but by a previously proved theorem. That 0 plus n equals n. And by the way, the statement of this theorem is for all n. It's only a coincidence that n happens to match. What this will do is see if there's a way to match the parameters of this theorem to some term in the conclusion. And there is. We'll have n instantiated by n. And now that's easy to prove by reflexivity. OK. Let's do this. Let's prove that for all n, n plus 1 is not equal to 0. And remember, we're in the natural numbers here. So let's see. We can, well, the definition of not is just implies false. That is, if we unfold not, which is negation, maybe it's this. There. We're really trying to prove that n plus 1 equals 0 implies false. So let's intro. Intro says, oh, make up some name for this, which will be h. And now we can simplify in h, which tells us nothing. So, so here's that proof again, done right. We're going to intro. Now, we're going to do case analysis on n. So this destruct tactic is a case analysis tactic. It takes an inductively defined thing here that we have, that's some term that we can talk about in this proof, and say, well, either it's 0 or it's the successor of n prime. And so here we give the names to the subterms that we want to introduce. When we do the case analysis, now instead of one proof goal, we have two. In the first proof goal, we have these hypotheses, and we need to prove false. And in the second proof goal, we have some other hypotheses which aren't shown in this display, and we'll need to prove false. So the first proof goal is where, let's go back one step. We had n plus 1 equals 0. We destruct n, and now we have 0 plus 1 equals 0. And we need to prove false. Now that 0 to the left of the plus is an actual constant, the case analysis in the definition of plus will simplify. So let's simplify in H. We get 1 equals 0. And here I want to turn off the fancy notation stuff. Right? We get the equality of successor of 0 with 0. And by the nature of an inductive definition, there are these two different constructors, S and O, and they're just not the same. No thing built with S at its root is equal to a thing built with O at its root. And the tactic that applies that kind of axiom is called discriminate. So we'll say this is observed by the discrimination of the constructors in the assumption H. And that proof goal then disappears. OK, now here's our other goal, that the plus of the successor of n prime with the successor of O equals O. And if we, since the left-hand argument of plus is a constant, now simplification will do the case analysis in plus. So now that's that the successor of something equals O. And again, we can discriminate in H. And our proof is done. OK. Now, here's the theorem you asked for. Let's do this. We introduce the n, and we simplify. But nothing happens when we simplify, because plus does its case analysis on the first argument, not the second. So what I really want to do is throw this away. But just to leave it in the proof script, I'll admit it, which is now we've polluted the namespace with an unproved theorem. OK. So let's try again. Let's destruct n. Now we have two cases. The first case is that n equals 0, which proves by reflexivity. And the second case will simplify. So watch what happens to the parentheses here. Simplify says the plus does case analysis on its first argument and sort of unrolls one step of the definition. And now we still need to prove that n prime plus 0 equals n prime. So this proof is inadequate. What we really need is something more powerful than case analysis. We need induction. So we're going to do induction on the structure of n. And so in one of the cases, there's no substructure of interest. That's the 0 case. And in the other case, there's going to be a subterm n prime of interest. So the first case is easy as before. And look at the second case. Above the line, we have the induction hypothesis, IH, induction hypothesis, regarding n prime, which is that, by inductive assumption, n prime plus 0 equals n prime. So if we simplify in the conclusion, and we rewrite by the induction hypothesis, we get something that's easy to prove by reflexivity. OK, so let's prove that n minus n equals 0 for all n. How do we do this? Well, it's a for all, so we can do an intro. Now we have n above the line. What else is there to do? We could do induction. We have to do induction on something that's above the line. The only thing above the line is n, so let's do induction on n. First case is simplifies to something nice, so that proves by reflexivity. And the second case simplifies, I hope. Yeah, Sn minus Sn simplifies to n minus n. And that's exactly our induction hypothesis. So let's apply the induction hypothesis, QED. All right. So here's another theorem. 0 plus n times m equals n times m. This would be easy to prove by the means I showed you already, but here I'll just show you the notion of asserting an intermediate fact in the middle of a proof. So I assert that 0 plus n equals n. I prove that intermediate assertion by reflexivity. And now I have a new hypothesis above the line. I can use that assertion, once proved, in the rest of my proof. So I can rewrite by that assertion and prove the goal. Okay, so here's another theorem I want to prove, that addition is commutative. So let's do induction. We'll do induction on n and simplify. Well, in the first case, n is 0, so that's easy. It simplifies, and we can apply that previously proved theorem that 0 is a unit on the right. So that's good. And in the second case, we have that n plus m equals m plus n by induction hypothesis. We simplify in the conclusion. And now we're stuck. This is a dead end, actually. Why is it a dead end? What have I done wrong? Yeah, well, so I mean, I can rewrite by induction hypothesis. That's fine. But something's wrong. Okay, so I'll show you what I did wrong. I have the wrong m here. Yeah. So here's what I should have done. Let's go back here. I do want to do induction on n, but I want to generalize m first. I want to say, well, I'm doing induction on n, but the induction hypothesis is not that n plus m is reversible. It's that for all m, n plus m is reversible. So what I could have done is just not introduce m, or if it's already introduced, I can say generalize. So I'll do that as follows. Instead of having m above the line, I want to prove something about all m. So that will be my induction hypothesis. And then I can now do my induction on n. And in each of these two sub-goals, now I can introduce the new m. And simple and apply, what was the name of that theorem? Plus OR. No, that wasn't the name of the theorem. Yeah, well, okay. Here's what I can do. I forget the name of the theorem I want to apply, so I can tell Coq to tell me all the names of the theorems it knows about natural numbers. And there's one. So yeah. All right. So let's now intro. This is the inductive case. We'll simplify. We will rewrite by the induction hypothesis. Is that what we'll do? I'm not sure what we want to do here. I shouldn't be stuck. What's wrong here? Do I also need an induction on m? It's possible. All right. All right, let's do an induction on m. Okay, that case was not so bad. Let's simplify in this case. I'm making a hash of this proof, but that happens.
Oh yeah, and then you pull off the S's.
Let's rewrite backwards by IHM. That didn't help.
Yeah, I think that was going well. You can pull off the S's.
Yeah, I can pull off the S's. So one tactic that helps pull off the S's is called F equal. You apply a function like S to equal arguments, and you should get equal results. So now that's that sub-goal, and that's, let's simplify in the induction hypothesis. Does that help? No. I can't believe I've made a hash of this simple proof. Yeah, well.
It didn't want you,
What?
What's the definition of plus?
That's the definition of plus. Now we're getting somewhere. All right. Well, I'm sure there's a much nicer proof hiding in there. But, you know, the advantage of these mechanical proof assistants is that you don't have to give the nicest proof. You just have to give a valid one.
Is there stuff that will help you clean out the cruft? In other words, to actually look to see some of the assertions you made that didn't get anywhere?
Oh, undoubtedly. I mean, some of these theorem provers have these kind of tree shakers that shake out the things in the tree that aren't actually attached. All right. Well, you'll have to forgive that clumsiness. Do I want to explain this? I want to prove this easy consequence of commutativity of addition. And so I rewrite by the theorem plus com. What do I really want to switch is the n and the m, but it gets the wrong thing. It switches the outer plus rather than inner one. So let me undo that. And just remark that I can instantiate plus com with some of its arguments so that it will match the particular thing I want it to match. And so let's rewrite the inner plus, the n plus m, and that proves by reflexivity. Okay, well, such logical things as Cartesian products can really be just defined as inductive definitions. So here's an inductive definition with one constructor, a pair, that takes two nats and returns this new type called natprod. So here's sort of a construction of pairs of natural numbers. And we can even define operators like choose the first element and choose the second element, these projections. And we can give a notation to pairs so that they look like our standard notation for Cartesian product. And then I could say, what's the first element of 3, 4? And it will tell me over there that it's 3. And I can make definitions like, this shows pattern matching on the fancy notation that, that swap the elements of a pair, xy turns into yx. And I think I want to skip these two theorems and talk about a different structure, which is lists of natural numbers. Well, in set theory, you would use your pairing constructor or something to make lists, but that's not really well typed in type theory. So let's make an inductive definition for lists of natural numbers, which has two constructors, nil, which is the empty nat list, and cons, which takes a nat and a nat list and gives us a nat list.
So that means it's sticking on the front?
Yeah, it's the cons is a kind of right associative operator. So there's a definition. Cons of 1 to cons of 2 to cons of 3 to nil. And we can make nice notation for it. So the colon is the consing operator that's written infix. And we can even make fancy bracket notation. So now all these things mean exactly the same object. But this, well, because we defined write associativity on the cons operator. We don't have to write all these parentheses, and we can even use this notation if we want to. Okay, and we can write functions on lists. So here's a function that takes a natural number n and another natural number called count, so two formal parameters, and returns a nat list, which Coq remarks is, what did Coq say? Repeat is recursively defined, decreasing on the second argument. And you know, if Coq can't figure out where it's decreasing, then it won't accept the definition at all. And what does this do? It makes a list of count occurrences of n. Pretty straightforwardly. Length takes a nat list, so now it's inductive on the structure of the list, and the empty list gives us length 0, and the list of head h and tail t gives us the successor of the length of t. And here's the append, the concatenation of two lists. And the nil list concatenated onto L2 is just L2, and the list head const tail concatenated onto L2 is head const the append of tail with L2. So simple in structurally recursive definitions. And we'll make up notation. Plus plus written infix is for list append. So the concatenation of 1, 2, 3 with 4, 5 is 1, 2, 3, 4, 5. Which is proved by this simple tactic of reflexivity, because reflexivity knows how to unfold definitions and simplify case analysis. And not much else, actually. So a nil concatenated with the list 4, 5 is just 4, 5. And 1, 2, 3, 4, 5 concatenated with nil is 1, 2, 3. Now, this is not because it does case analysis on nil here. It's because it keeps unfolding the case analysis on its left-hand argument. And we can define functions like head. The head of an empty list gives us a bogus result, and the head of any other list gives us a useful result. And tail, ditto. So the head of the list 1, 2, 3 is just 1, proved by simplification, reflexivity. And the tail of the list 1, 2, 3 is 2, 3. So here's a theorem. Nil appended to L equals L. Proved by reflexivity. And here's one. The predecessor of the length of L is equal to the length of the tail of L. And for this, we need to do case analysis on whether L is nil. This works because the predecessor does the same bogus thing on 0 that the length function does on nil. So as long as our bogus definitions line up properly, then the theorems are stated elegantly. Okay, and so L is either nil or not, and if it's nil, then this simplifies to 0 equals 0, which is proved by reflexivity. And if it's not nil, then this simplifies to length of L prime equals length of L prime, right? Because this length simplifies to successor of something, and the predecessor of successors simplifies to the thing, and on the other hand, vice versa. So this is an easy proof. Now, Coq generates an induction principle for every inductive definition. So now we can do induction on lists, not just induction on natural numbers. And by the way, here is the induction principle on natural numbers. Which says that for every proposition, for every predicate P, that is for every function P from nat to proposition, if P holds on 0, and if for all n, P of n implies P of the successor of n, then for all n, P of n. Well, Coq generates this induction principle because, in fact, here's a proof of nat end as a term. Here's the term. It's not a very interesting term. It's lambda p dot natrect t of p, so I should print natrect t. This is pretty horrible. This is sort of the raw calculus of inductive constructions. So underneath all this, there's a logic. Everything I'm proving with the tactics is actually constructions of terms in the underlying logic that are checked by the kernel of Coq. So the tactic system may or may not have bugs in it. The kernel is expected not to have bugs. And in fact, I want to skip to the end, because I'm running out of time, not the end, but what do I want to remark here? I showed you this constructor natlist for lists of natural numbers. What we really want is a list constructor parameterized by the type of the element. And this kind of parameterization by types allows us to make much more general theorems and definitions that we can then apply to many other types. So our library of theorems about list concatenation should be general to lists of anything. The type parameterization in the calculus of inductive constructions permits that. I want to briefly show you something about inductive definitions of propositions. So before I showed you inductive definitions of data structures, like natural numbers and lists, here is an inductive definition of a predicate. Evenness is a predicate that is a function from nat to prop. And when you say inductive, what you're doing is axiomatizing something. That is, this evenness predicate, we know two things about it. We know that 0 is even, and we know that if n is even, then successor of n is even. And that's all we know. So that's a kind of inductive axiomatization. Now, one of the kinds of techniques that we use is proof by induction over the derivation of a fact, right? So there's Ev. Here's the induction principle for Ev. Let's see. For any induction hypothesis P, if P holds on 0, and if for any n on which Ev holds and which P of n holds, then P of the successor of n holds, then P holds on any Ev number. So this is a kind of proof theory, right? We have a fact of Ev. It must have been derived somehow using these axioms, and we can actually do induction over the structure of that derivation. And that's an important method. Now, this is the induction principle, and when we write down when we say the word induction as a tactic, what Coq does is figure out for us all the details of applying this induction principle, and it tells us what all the appropriate subgoals and hypotheses of the proof are. But where did this induction principle come from? Well, let me print the induction principle. Again, it's a construction. This is the construction in the calculus of inductive constructions, and this is the type. So the kernel type checks that this term has this type. Well, the type is the statement of this theorem. So this is back to the Curry-Howard isomorphism, that the type of, that a proposition is viewed as the type of all of the different proofs of that proposition. Here's a term that is the proof of this proposition. The proof assistant says, oh, you can just write down this, which is a friendlier notation, and I will figure out what induction principle you meant, and I'll figure out the proof of that induction principle. And similarly, in the middle of proofs about natural numbers, I'm going to import the Coq Arithmetic Library, which has lots of lemmas that I don't have to trust because they're proved and checked by the validity checker, and decision procedures. So here's the omega decision procedure. Omega is an algorithm invented by Bill Pugh 20 years ago at the University of Maryland for compiler optimizations about array indexing. Here's a theorem for all x, if x is x plus 5, for all x, x plus 5 is greater than x plus 1. So, I could probably figure out which lemmas to apply in the theorems about natural numbers. And it would take me, 3 minutes. But why not just dump this into a decision procedure for inequalities on Pressburger arithmetic, and it solves it. Well, you know, it's overkill to apply this fancy decision procedure for inequalities on Pressburger arithmetic to that, but on the other hand, it only took me 3 or 4 seconds to type omega period, and my time is more valuable than the computer's. And by the way, if you didn't trust the omega tactic, here's the completely horrible and inelegant proof that it made for the fact that x plus 5 is greater than x plus 1. And it's the application of valid terms that are all checked by the validity checker. So, you know, we have the computer here. We should use it. OK, well, that's all I have time to say in 50 minutes. So, yeah, much of my life is sitting there proving theorems in this proof assistant about the operational semantics of programming languages and compilers.
So how far can this go? I mean, can you give an example of a complicated theorem?
Yeah, I gave some examples.
Okay.
Yeah, right. So my complicated theorem is that when this static analyzer, which is several thousand lines of program code, tells you a certain property about this program, and then you compile this program using this compiler, which is several thousand lines of program code, to a machine language, and then you execute that machine language on the PowerPC processor, it will have the property you specified in the source language. That's my kind of theorem. Now, that theorem is complicated enough to state, because by the time you've unfolded the statement of that theorem, there's all sorts of stuff in there about the machine and the compiler and so on. And it's not sufficiently mathematically interesting to prove all of those things that you could get a referee or a graduate student to sit there for a year checking all the steps. But you can get Coq to sit there for 20 minutes checking all the steps. And then that theorem has application in the world of engineering, where people are concerned that this system for deciding whether some private in the army is authorized to download that stuff, you know, is actually correct. And
if we go back to, let's say, the example of the four-chord theorem.
yeah.
So you said that in 2005, maybe this was based on the proofs of Appel, and of Seymour.
Yep.
Robertson et al. So this is how automatic
Well, so in other words, Gontier worked for a year or two formulating the statement of that theorem and then working step by step to construct the proof. And he did some very sophisticated proof automation so that he had decision procedures and algorithms that would help construct the proof that would be checked by the Coq kernel. But these two proofs were based on, well, there's the reducibility part and there's the, what's it called? Yes, the discharging. Well, no, the reducibility and the unavoidable set, right? And in the original proof, the reducibility was checked by computer and the unavoidable set was checked by hand. Well, in the second, both were by computer, but why should you trust that computer program, right? And so the difference between this proof and this proof is that the only computer program you need to trust is this Coq kernel, which is a general logical type checker for validity in the logic. And every other part of the computer program that Gontier wrote based on their computer program, he proved the properties of in this kernel. So that's sort of the difference. Yeah.
I was meaning to ask about the second example, Rosler.
Mm-hmm.
For real? Because did Coq do arithmetization of syntax?
No, Coq doesn't do anything.
So
You
what
formalize
do you
everything.
mean by that? Because if you do arithmetization of syntax, then the length of the sentence is too long for even Coq to handle. So what was done there?
Well, if you look at, so first of all, I haven't read this in detail, but I've done Gödelizations. So not in any of these, but in the first project I talked about with all the, you know, I've done Gödelizations. And if you look at Gödel's proof, he demonstrates that things are Gödelizable. but it doesn't show you every last bit of the formulation. So what you do is something similar. You prove, you state in the logic.
Yeah, you show that the diagonal function is formalizable, representable in PA. So this won't do that.
As I said, Coq checks that this guy properly formalized. Well, let me rephrase that. This guy
Formalization is correct. But
well, there's going to be a statement of a theorem somewhere, and so there's going to be definitions leading to the statement of the theorem. And Coq will check that those are well typed, but it won't check that they're the theorem you meant to prove.
yeah.
And once you state that theorem, if there are godelizations in there that are part of the proof and not present in the statement of the theorem, then Coq will check that you've done something correct in logic.
And the one other thing, why do you stop at natural numbers? Why don't you say add the type called limit ordinal and do it and prove that?
Well, I stop at natural numbers because I have an hour,
No,
right?
but can you do that? Can you
so-
add the type called say ordinal and prove that every second ordinal is even?
Yeah, well,
You will start with 3, 0, and limit.
let me give an example, let's say the real numbers, right? So there are the constructive reals, which are not quite the reals because there are only a countable number of them. But now that you have co-inductive sets, and I'm stepping like epsilon beyond what I'm actually sure of here. But there are real number libraries in Coq, and they generally work by saying, okay, let's make an inductive set of infinite sequences of something. Now, John Harrison's construction of the reals doesn't use the standard sort of limit construction. He uses infinite sequences of A over 1 plus B over 2 plus C over 3 plus D over 4. And he constructs the real numbers and proves all the axioms of the real numbers. And so somebody, I believe, has translated roughly that proof that he did in the Hall system over into Coq. So especially with the co-inductor sets, you can reason about constructions that aren't necessarily countable. I don't know what people have done with ordinals, but the reals is a good enough example. Yes?
So it would be cool if an entire college textbook were formalized. And it seems that there's no technical or mathematical obstacle to it. So it's like a sociological obstacle, right?
Well, people are doing that. But people are doing that.
It's more an HCI question, but how can you make it more fun so that more people will want to do it?
Oh, well.
Huge open source software, projects.
Yeah.
Made by
So
volunteers. So what's the sort of sociological obstacle to doing that?
I don't know, but people are doing that, not just in Coq, but in other theorem provers. Now, I teach a course on the operational semantics of programming languages and type systems for programming languages. And that course has been taught at Princeton for, 15 years or so in that form. And for the first dozen years, it was taught either by me or by Dave Walker as, let's write down inductive formulations of predicates on the board, and then let's do proof theoretic reasoning over these terms. And there's a bunch of undergrads who have never done proofs before and who turn in a homework every week that's wrong, and the wronger it is, the harder it is to grade. And they learn not enough, and they do induction over the thing they're proving rather than the assumption they have. All right? But for the last 2 years, I've taught this in Coq, based on the textbook that Benjamin Pierce at Penn wrote. And at the beginning, well, what I gave you is sort of a summary of the first 6 lectures in that course. So they first learn logic and how to prove things in logic, and the proof checker checks their every step. And by the end of the course, they're doing fairly sophisticated proof theoretic proofs about operational semantics of programming language and soundness of type systems. In the middle, I give them an actual proof to do in class by hand without the proof checker, and they realize that they should learn something about what it is they're doing that way too. And Vladimir remarked to me, especially take that example that I botched, where I had to properly generalize over M, right? The undergrads get very good at this, of properly stating the induction and generalizing over the things that need to be generalized. And he says, well, these undergraduates are doing intricate proofs by induction that mathematicians usually don't trust themselves to get right. Okay? So the answer is when there's an application for it, and in computer science, the applications for very formal logical proofs tend to be in the formal methods in both hardware engineering and software engineering, then it's not difficult to motivate the students to use the proof checker, and they have a lot more fun doing that than sort of blundering around with no idea how to do proofs. So I had 50 students in this class last year, about 40 undergrads and 9 grad students and 1 Fields medalist. You know.
Did he pass?
Well, you know, it's a big room, and when you have 30 students and you ask a question, then somebody will answer it. And you have 50 students, either the bright sophomore in the second row would answer the question if I asked it in lecture, or that guy in the third row would answer the question, and he seemed to get it pretty well. Yes?
To what extent do you think mathematicians should use formal proof verification?
If they want to. I'll tell you this. This kind of result I did not do early in my career. I am not a good enough mathematician to get results of this sophistication and get it right and stay motivated unless I have the proof checker to keep track of all the stuff for me. So I can now do a kind of mathematics in the semantics of programming languages that I was not able to do without the tool. Yes?
I spend a lot of time reading other people's proofs and trying to understand the main idea so that I can do something related or similar. Do you think that is harder if the proof is written in Coq, or the same? Or
well, in the Coq with the syntactic language that I've been showing you, you can generally read the statements of all the auxiliary lemmas, because they're just written in math, translated down into ASCII. And then the proof scripts are unreadable. Okay, although if the statements of the lemmas isn't enough to explain to you what's going on, you can actually step through the proof scripts to see what the intermediate hypotheses are in the interactive system. Now, there are people out there that are designing and have designed proof scripting languages that they claim are more mathematical and more readable, both for Coq and for other proof tools like Isabelle Hall. And I'll withhold judgment because for me it's useful enough that the intermediate lemmas are quite readable, and that you know, it would be good if the proof scripts inside the lemmas were readable, but it's just not important to me. Yes?
You mentioned this co-induction, so how roughly does that work?
Well, so instead of the word inductive at the top of your definition, you say the word co-inductive. And now the induction principle is a little different. It's a co-induction principle. And the tactic is co-induction instead of induction. And I've never used it. And the people I know that have used it say, well, if that's what you need, that's what you have to use, but it's just harder to use than induction.
So what is co-induction then?
Oh, it's how do you reason about an infinite sequence of natural numbers? Well, there's some sort of induction principle, but it's not an induction principle because it's not well founded. It's a co-induction principle. So that's some fancy thing in logic that you might imagine, but I can't explain. Because, you know, I learn logic as needed, right, to do my stuff. And since I have never yet needed co-induction, I haven't learned it. Yes?
How much work there is done on the decision algorithms?
Oh, lots. Yeah, so there's a whole branch of computer science where people are working on decision procedures with application to proof assistance and to program analysis. So omega, which is reasoning about inequalities in Pressburger arithmetic, is one. There are Boolean satisfiability solvers. So, you know, what we learned 30 years ago is that satisfiability is NP complete, so one shouldn't write programs to solve satisfiability. But 10 years ago, some electrical engineers who didn't know that designed some very good algorithms that have been improved, and now satisfiability is considered an easy problem. right? It's not that the worst case instances are easy, but the practical instances that come out as, you know, I'm in the middle of proving something, and I want to see if that instance, which is not a typical worst case instance, it's an instance that came out of some proof that had some structure that I was thinking about, is solvable. Boom, it's solvable. So satisfiability. What other interesting decision procedures are there out there? Well, satisfiability modulo theories, that is modulo axioms about equality. Integer linear programming. Well, linear programming. If I have things that are sort of expressed as linear programming instances, they get solved. But even when they're restricted to the integers, which is NP complete, no problem. There's good solvers for those now. So there's all sorts of, and there's a lot of research in taking these algorithms and making them generate witnesses, that is, proof terms in the calculus checkable by some kernel, so that even if you didn't trust this algorithm, because it's software, it generates a proof that can be checked by the kernel that you do trust. And you only trust a kernel because, well, it's pretty small. It's a small program that you can actually reason about and write peer-reviewed papers about. And it implements an algorithm for validity checking in some logic that people have written peer-reviewed papers about, and so on. Yes?
So how efficient is Coq? So for example, in the four-color theorem, you know, once he got all of the things, how long does it take Coq to actually verify that?
A minute or two. You know, this took, I think he said it's about a minute or two or 15 minutes. You know, this proof, the checking took something like, you know, 1,000 hours on a big IBM. So that means it should take, you know, 1/10 of a second on this thing, right? Yes.
So when you have many of these tactics, you have to be careful about which tactics you activate simultaneously so you don't get into looping sorts of things.
Oh, well, when you're in the middle of proofs, you get into dead ends all the time, because that's, you know, proof. And if your tactics loop, then you never get to that QED. I don't know what the, you know.
I see. So they're, right, okay. Because I just remember things from like where you did the wrong sorts of things. It sort of started. There were certain options.
Yeah, right.
That would get you to
the tactic language is itself programmable. So I write new tactics all the time, programmed in terms of the existing tactics. And often I write these new tactics and they get into infinite loops, and I have to kill it and start over with a better designed tactic. But the advantage of automating the tactic is that certain kinds of repetitive structures that come up in my proof are just solved automatically. Yeah.